Show your program. Representing. Hello, Aditya. So you open this kth smallest. How you have done that? You tell me. No, recursively, how you are finding the median of median? Recursive calling where? No, you have grouped it into 5, okay? Then you have found the medians of all groups, and then where you are calling there itself. So recursively you are calling. Median of median. Okay. No, if I tell you, then you run. Okay. Next is Arindam Padia. Yes. Arindam. Hmm. 35 students are there, 40 students are there. So I am taking again one attendance, and those 5 students, Saurabh, you tell those 5 students to call me immediately. I will be telling you who are those 5 students. I am taking one more attendance. Next, Arindam is not there, I guess. So I'll check in the list whether you are there or not. Sorry? Arindam. You are there, I guess. Okay, connection not good. Charan Malla. Show me. Come up with your laptop then. Make the mobile as the hotspot and then you connect it to the laptop. No, these alibis should not be accepted, okay? So you won't be getting marks then. Whatever. You have done it in mobile. So how can you show that? So you show me you have done. No. This alibi is not accepted. Hush. Next is Hush. Are you there? How many? Which are the three? Show the Karatsuba one. Where you have done this? You run it to your machine, in your machine. You run it in your machine. You run it in your machine. No, this is in cloud you are doing? How can I be sure that this is your program? Where is the name? Where is your name? Okay. The Karatsuba, how you are doing? Hmm. Okay. So Ishan Datta. Ishan Datta. Show your code. How many programs you have done? Where? Closest pair, how you have done? Where you are implementing that that for considering a point you are checking at most 12 points or 6 points, where you are implementing that? Ishan Datta, what happened? Network has lost. Network. No, it's not okay. Audible. Okay, so today up to this, and I am now presenting. So you remember that any day your term might be coming. Okay, so you be prepared, and those who are leaving, okay, those who are not joining the class, okay, I guess you are almost 50 odd students, but not attending. Okay, so I'll send a report to the authority. What you people are doing, I don't know. Okay, so I am presenting now the greedy algorithm we were discussing. Okay. And that we can continue a little bit today for the remaining time. Is this screen visible? Is this screen visible? Am I audible? Okay, so you're discussing that interval partitioning algorithm. Okay, and this is from this KT book slide and that Princeton that algorithm course. Okay, slide. Okay, so this interval partitioning we are discussing, and we are discussing that, okay, if I am having several overlapping jobs, okay, several overlapping jobs, and then we have to schedule all the jobs. Okay, we have to schedule all the jobs. Then with how many rooms, or if these jobs are the, so we discussed that these jobs are the classes, okay, class durations, and we are having resources, that is classrooms. So jobs and resources. So if overlapping jobs are there and we are having some resources, multiple resources we are having, on demand we can access the resources. Then how many resources will be requiring to schedule the job? Okay, So we have seen that, okay, several templates we have checked. So finish time, then shortest interval, then fewest conflicts, okay. None of them giving the optimal solution. But if we are going by this start time first algorithm for this case, in the interval scheduling, we had the job sorted in ascending order of finish time, and then we are scheduling the job, and then we are keeping as much time as possible for the remaining jobs to be scheduled in the previous case. But in this interval partitioning, right, we are having resources. Okay. On demand we can access the resources, but we have to find out that how many minimum number of resources will be required for scheduling the overlapping jobs. Okay. Scheduling the overlapping jobs. So that is our criteria in interval partitioning. And here this earliest start time first algorithm will be optimal. Okay. Earliest start time first. That greedy template will be working fine. So this is our number of jobs, and for each job this is the start time, this is the finish time. Okay. So likewise for all jobs, that will be taken as the input, right? And then we are sorting the jobs in ascending order of start time. Okay. Ascending order of start time, and based on that we will be scheduling the jobs. Okay. So this is the number of classroom. Number of classrooms will be initially 0. That means no job is assigned till now. I have started. I have started earlier. I was recording your presentation. But thank you for reminding me. I may be forgetting. Yes, there is a possibility. Okay, for J equal to 1 to n, that means for each job, if lecture J is compatible with some classroom, schedule lecture J in any such classroom K. Okay. So if J is compatible with the classroom, so initially we are having one job, and that is the first job. So we will be invoking one classroom, say classroom 1, and we will be scheduling that. Okay. So else, if it is not compatible, say I am considering, say this is job number 1, this is our job number 2, this is our job number 3. Okay. And if lecture J is this, so whenever I am considering the next this job, okay, so this job J, whenever I am considering, if job J is compatible with some classroom, so this is overlapping job with this earlier scheduled job, earlier scheduled class. So this is not compatible. So in the else part, in this case, else part will be activated. And here what we will be doing is we will allocate a new classroom D+1 first. So we will be allocating this job to classroom 2. Okay. So this is classroom 2. So I can give the classroom as 1, 2 in different color. So this is, and this job number, this is job number 1, this is job number 2, something like this. Okay. So this is in classroom 2. We have to invoke another classroom because we cannot schedule this job in classroom 1, because classroom 1 already has allocated this job. Okay. So you have to allocate a new classroom, that is D+1. That means how many classrooms we have allocated right now? So 2. So second classroom. And schedule lecture J in classroom that D+1. So this job will be allocated to classroom d plus 1, that is 2. And then we have to increment that d to d plus 1. That means how many classrooms we are now scheduling with 1 and 2. Okay. And then we are having this job to be scheduled. Okay. So in this case, you see this job is compatible with 1. This job is compatible with 1. So whenever this job I'll be considering, so at that time we have one classroom where I can schedule this job number 3. So in classroom 1, I have to schedule that job. Okay. So this is job number 3, right? So I can give it another color. Job number 3. Job number 3 will also be allocated in room number 1, and room number 2 will have job number 2. So this is the scheduling algorithm example that we have got here based on the algorithm given here. So this is the earliest start time first algorithm, and whatever schedule we are having, you have to return that schedule. Okay. So now the thing is that this earliest start time first algorithm can be implemented in order of n log n time, right? Earliest start time first. So we are trying to measure the time complexity of the algorithm, time complexity, and it is claiming that okay, we can do it with order of n log n time, right? So to do this, what we got to do is we have to maintain a priority queue. We have to maintain a priority queue, store classrooms. We have to store classrooms in a priority queue. Okay. That is key equal to finish time of its last lecture. Finish time of its last lecture. So this to determine whether lecture J, so this is required for the compatibility issue checking. Okay. So to determine this whether lecture J is compatible with some classroom, and then this we can compare the start time of that lecture J under consideration to key of minimum classroom K in priority queue, right? In priority queue. That means those are the classrooms which are occupied now. Those are the classrooms which are occupied now, right? So those classrooms we can or the classrooms we can store the classroom information in a priority queue. To add lecture J to classroom K. Okay, so this may not be requiring. So this, what actually we are trying to do is, say this earlier example I am taking, earlier example here, and another one, this job was there, and another job we had like this. Say this is 8 to 10, right? And say this is 9 to 11, right? And say this job is what? This should be 10:30 to say 11:30. Okay. Okay, so these are the jobs we are having. So now this we are storing this job first in classroom 1, right? In classroom 1 we are scheduling that job. And then what we are doing is the finish time of its lecture, last lecture, we have to take that into account. So that is 10. We have to store the this information in a priority queue. Okay, in a priority queue, and that this priority queue implementation is here. We are looking for this finish time of its last lecture. Okay, and minimum classroom K. That key is the minimum. Okay, minimum one. That means mean heap we can use. Mean heap. So if this is 10, okay. If this is the finish time of this lecture, then this is one node we are having that will be stored in this mean heap. Okay. So this mean heap. I think this heap in your data structure class. You have studied this heap, right? So that's why we are not discussing this heap right now, assuming that heap data structure. Okay. So this mean heap, it will be storing the mean heap. And now this, you see this, whenever we are having the next job that is scheduled, right? So then what we have to do is we have to compare the SJ. We have to compare the SJ. That means this 9. 9 is the SJ now. The next job to be scheduled. That compare this SJ to key of minimum classroom K in priority queue. So only one node is there. So we have to compare this 9 with this 10. Okay. So if this would have been greater or equals to this, then we don't have any this overlapping issue. Okay. They would be compatible, right? But as this 9 is less than this 10, then we are clearly seeing they are overlapping. Okay, right? So now we have invoked another classroom and we have entered that classroom number 2 here, and we have stored that classroom in that classroom number 2. Okay, but here you see this 9 and 11, so this is the finish time 11. Okay, finish time. So now this 11 we have to store in this heap, right? In this heap, and this is the mean heap. So the mean heap is that the root is always greater or equals to the children, right? Root is always lesser equal to the children for this mean heap, and max heap is the opposite. Root is always greater than the children. So maybe this we can store this 11 here. So this is not binary search tree. Okay, this is the heap. So this 10 and 11 is stored here, and the root is minimum of all, right? Minimum of all. So this is the criteria of storing the lectures by its finish time. Okay, by its finish time. So this is the finish time of its last lecture. Store classrooms, and now what we got to do is we have to compare the next job to be scheduled, that is SJ, its start time, whether it is compatible with the others. Then if I am storing with this heap data structure, then what will be happening? Then whether that SJ is overlapping with the jobs which are scheduled, okay, then only if I am comparing with only the root, then our job will be done. That's why we are using this priority queue. Okay. That's why we are using this minimum priority queue. Because if this Sj is not compatible with this 10, then it cannot be compatible with this 11, because the job which is having 11 finish time, it cannot be compatible, because this Sj is not compatible with the finish time 10. Then how it can be compatible with the finish time 11? So that is, if by finish time, if we are storing this, then only if I am checking this root 1, then our job will be done. So that's why this priority queue is important here, right? So now if this root is not, if this is, I am checking this, and then I am seeing, okay, it is, so whether it is compatible or not. If it is not compatible, then we have to store it in other classroom. Okay, like that. So this and what we got to do after getting the next lecture, we have to store that finish time information into this heap. Okay, so at that time we have to adjust, we have to make it a mean heap as well. Okay, so in that case, to insert an element into the heap, that will be taking log n time, order of log n time. So how many such priority queue operations could have been there? So for each of the jobs, we might have to do all this information, all these insertion operation, and each insertion operation will be taking order of log n time, because that will be reheapifying the main heap. Okay, so this order of log n time will be necessary for each operation. So this order of n number of such operations might be required. So this will be requiring order of n log n time, right? This will be requiring order of n log n time, and by that we have processed all the elements, that means all the jobs we have processed. So we can claim that our algorithm will be running in order of n log n time. Okay, so that's why this priority queue implementation is there. Now if you don't know this heap, then I can take one more class on heap. Okay, you know heap, all of you know heap data structure? Not properly? Okay, so for the time being, you have to take into account that this is this heap data structure is a very important data structure for priority queue, and priority queue operations happens in many different algorithms. Okay, many different algorithms. So that's why heap is really important data structure. And also with this heap we can sort the elements in order of n log n time. Okay, so I may take this heap at some point of the lecture if time permits. Okay, so this order of n log n time, we can store all the classrooms and we can schedule all the classrooms. So that is this is the proposition here. That means this is the theorem. Okay, already proved theorem is called the proposition. Okay, now another thing we have to take into account, that is the depth depth of a set, say, now we are trying to prove that our this interval partitioning algorithm with start time first is optimal. Okay, is optimal, right? That means with this start time first, we can schedule all the lectures with minimum number of classrooms. So we are defining one term that is called depth. Depth of a set of open interval is the maximum number that contain any given time. That means how many jobs are overlapping at any given time. That means maximum number. So you see here we are having 3. Here we are having 3, right? So here how many jobs we are having? We are overlapping. So this is 3 jobs overlapping here. So at this point 3 jobs overlapping. So at this point 3 jobs overlapping. Okay. So if I am doing my own, so this is one job. So this is another job. Okay. This is another job. Okay. So now this is another job. Okay. Just we can have this. Okay. So at this point we are having 3 jobs overlapping. So at this point, how many jobs overlapping? 2 jobs overlapping. So at this point, how many jobs overlapping? 2, right? So here the depth is d equal to 3, right? That is the maximum number of jobs which are overlapping at any given time. Okay. And definitely one key observation is that, just a minute. One key observation is that definitely this number of classroom needed, that will be greater equals to depth, definitely. Because if this guy is overlapped with this, we cannot schedule these 2 in the same classroom. So all these 3 classrooms, all these 3 jobs are overlapping. So we need 3 different classroom for this, definitely. So number of classroom needed, that will be greater equals to the depth, right? And does the number of classroom needed always equal depth? And that is yes. Okay. That means if we are going by this earliest start time first algorithm, then we need these many, only this d equal to 3 here, this with 3 classrooms, earliest start time first algorithm will be scheduling our jobs. Okay. So you see this our earliest start time first algorithm. So you see that we can give a rough argument like this. Okay. This, if I am having if the jobs which are overlapping, okay, I can write like this. Okay. If the jobs are overlapping like this, say, so if the jobs are overlapping, so whenever we are starting at any point of time, here some jobs might be there, here some jobs, okay. But at this point, say I am considering, and say whatever jobs we are overlapping here, say D is the maximum one, right? So as long as this D will be continuing, as long as this overlap will be continuing, then we need D equal to maximum number of classrooms. So once it is coming out, then we need, say at this point we need, if that is not maximum, then at least one job, one classroom that we are leaving out, so that if any further job is to be scheduled, we can schedule in this classroom, right? So in that case, at this point D-1 classrooms will be activated, one classroom will be vacant, okay, and we can schedule that in our algorithm, okay. So this so what we can argue is this: as long as the overlap is there, if assuming that D equal to the max, okay, so as long as overlap is there, so this D classroom will be sufficient. And if overlapping, this lesser number of overlaps will be there, then some other classrooms will be definitely vacant, so that we can schedule others. There cannot be, so if I am arguing that okay, there might be say here these 3 overlaps, okay, these 3 overlaps, and I am claiming that if this is not the max, then I am telling okay, I might be needing, that means I am having some more overlaps, okay, some more overlaps, then already I have assumed that D is the maximum one. So if some more overlaps are there, then that would have been the maximum, okay. So that will be contradicting the fact that already we have got the optimal D, right? So we cannot have the more overlaps, right, beyond that point, or this before that point, because D is the optimum. So that's why this argument is showing that okay, this earliest start time first, this is a rough argument, that earliest start time first algorithm will be the optimal one, right? Okay, so this is interval partitioning. You can go by this proof here given, and that will be following our argument almost. So in the next class, what we'll be doing is we'll be doing this scheduling to minimize the lateness, okay, scheduling to minimize the lateness, and there we are having the jobs will be having this TJ amount for completion, TJ amount for completion, and DJ will be the deadline for that job. That means, say if I am giving one assignment, that assignment maybe it will be requiring 2 hours of time for you to do that, so that will be DJ, and I am telling that job, that is the assignment, you need to submit within 9 days, okay, within 9 days or 9 hours, right, 9 hours, say, or 2 days to complete that assignment, 2 days will be requiring, but the deadline is DJ equal to 9 days, right. So each job will be having a processing time TJ and a deadline DJ, and we'll see that what is the question that we'll be solving in this problem in the next class, okay. So in the previous case, that interval scheduling algorithm, we had a job with start time SI, say, and a finish time FI, okay, start time and a finish time. Here I am telling okay, that job may be starting from any day, but it will be requiring 2 days after that. So this is the subtle difference between this thing and this thing, okay. Okay, so today up to this, and in the next class we'll be discussing the other things. Okay.